So the first situation here that we're looking at to get beyond some of this biaxial stuff is a pressure vessel, all right? And we went ahead and derived the equations for the stress in a pressure vessel tank wall. So if you were to design one of these or analyze one, these equations hold for thin-walled pressure vessels, meaning the thickness of the wall is less than the radius of the tank is less than the radius of the tank over 10, okay? And what we did there, we kind of split the tank down the middle the long way as though it's a pipe. So we are ignoring the caps on the end, but that leads to a more conservative design, which, you know, is fine. That's often how we like to approach these equations, is to take conservative assumptions. We get the stress in the tank wall is P, the pressure times the radius divided by the wall thickness. It's called the hoop stress. So it splits the tank the long way, like that. To remember that, I just remember the hoop on a barrel, you know, because that contains that outward stress around a barrel. Okay. There's also the axial stress, which tears the end, or attempts to tear the end off the tanks. That's PR over 2T, which is the hoop stress over 2. So that would tear the end off of a tank like that. So then we looked at a situation here on 570. We have the pressure, the radius, and the wall thickness. We filled those in. We found the hoop and the axial stress. Okay. So 48 megapascals for the hoop. The axial is half the hoop, it's 24 megapascals. The hoop is the design stress. So if you're designing that tank, that's what you're designing it for, to contain to withstand that stress, okay? That's what you design it for. We also then, you know, this is a good example of kind of where this biaxial stuff comes into play. Now you can start doing a little bit of a biaxial analysis. So to accomplish that, you want to put those stresses on a rectangular section cut out of the tank wall. And they'll look like that, okay? So 48 would go in the Y direction in this case because the hoop stress is going in the Y direction. 24 is the axial. This is because the tank is laid out flat, okay? So the hoop is going that way in the Y direction in this case. The axial is going that way, tearing the ends off the tank. Okay, so the hoop is trying to split the tank in half the long way. The axial is trying to go the other way, okay? Now, if you've got a tank, you know, and I've seen a lot of tanks laid out horizontally, but I've also seen them laid out vertically, right? You know, there's one that's vertical. You know, they just design one to fit. They got a certain site. They got to match the site. So this one, they figure they put it in vertical. Now, when they do it that way, what's going on? Which way is the axial act? X or Y? Like that, right? So what I'm getting at here is the hoop and axial will change X and Y just depending on how the thing's laid out, okay? So if it's laid out that way, then the hoop acts that way, okay? It just depends how the tank's laid out, okay? All right, so we start with this biaxial element, and then from there we can do biaxial analysis if we want to. Let's find out what the maximum shear is, okay? Now, I already mentioned that there's no shear in the X and Y directions, and so the hoop and axial are the principal stresses, but there is shear at angles, okay, in that tank wall. It doesn't occur in the X and Y directions, but it'll occur at different angles in there. So what's the angle that you're going to have the maximum in-plane shear stress? What is it? If we know the principal angles are 0 and 90, what's the shear angle for maximum in-plane shear stress? Yeah, 45, yeah, okay. So we could run the numbers and find what the shear stress is at 45 degrees. And that will get us the maximum in-plane shear stress, okay? Okay. So we just do that. And we get, when you run the numbers, you get 12 megapascals, okay? And at 45 degrees, I get positive 12. The average normal stress is 24 plus 48 over 2, it's 36. So now I'm starting to see what's happening at different angles in there. I started off with these design equations that got me the hoop and axial normal stresses. Now I can go in there at any angle I care to find out about and start to figure out what the stresses are. All right, so what I found there is the tau max in plane is 12, positive at 45 degrees. And the average normal stress, which would be the normal stress on those planes, is 36. Okay. So there you go. We'll put them on there. We got normal stress at 36, pulling out in all four directions, and then we have on our reference plane that we're looking, or at the plane we're looking at, which is the 45-degree plane, which would be this one, because remember we measure the stress from the vertical. That's 45 degrees. The shear on that plane is a positive 12, so that would rotate that element counterclockwise, and then I build the other shears from there. So there's my in-plane maximum shear stress plane. Okay, you good with that? Okay. All right, now let's say we're going to design this thing though. We want to know what shear do I have to design it for? Now, if you remember from the biaxial stuff, there's also that out-of-plane shear stress you got to consider, right? Because tau max is equal to plus or minus sigma max minus sigma min over 2, okay? All right. So what's sigma min in that tank wall? What's the minimum normal stress? It is sigma z, right? 0, okay? Because we got the hoop and axial are 48 and 24, but the absolute maximum is in the z direction at 0. Now, actually, I'm going to put a question mark there because I'll come back to that, but let's use that. So what's tau max then? If I use 0 there, and I'm going to use something else, I just warn you, leave a little room on your page. Be 48 minus 0 over 2, right? It's 24, okay? You all good with that? So you got to be a little careful here. See, you can't just go in plane. The out of plane shear stress is twice what the in plane shear stress is. So if you end up working for Acme Pressure Tank Company, you might want to remember that one, okay? You got to double that. And actually it's a little bit more than that, as it turns out, okay? Depending on how you want to analyze it. And, you know, when you're doing this stuff, you often analyze conservatively, because you could almost argue, I don't know if I entirely agree with this, but I've seen this done, that in the z direction to that tank wall, remember the z direction is coming out of the page. There's actually a pressure pushing on that tank wall. You could think of that pressure pushing on the tank wall as being sigma z. So instead of being 0, sigma z is that, what is it, 800 kilopascals? If you look at the top of the page. If you really want to get even more conservative, don't assume sigma z is 0. Assume it's a compression of negative 0.8. And if you do that, you get even a little more shear stress. Okay. Now, I don't know if I entirely agree with that, because to really consider that, you have to also consider the fact that the tank wall is curved slightly, which leads to a few complications. But anyway, you know, and we're talking from 24 megapascals up to 24.4. Okay, so it's not a huge difference, but I have seen analyses that do it that way. Okay. So you might think of the absolute maximum shear stress in the tank as being actually plus or minus 24, or even if you want to take it out this far, plus or minus 24.4, because you're going 48 minus a negative 0.8 over 2. So, you know, whatever. Okay, so we kind of do this basic design equations. We get sigma max and sigma min, And then once we have them, we start to, you know, sigma max and min are the axial and hoop stresses, and then we can go in and just start doing biaxial stuff. Now the other thing we can look at is, let's just do an element here at 30 degrees clockwise from the vertical plane. Let's find the stresses on that element. Okay, just for fun. You might say, well, why do I want to know the stress on that element? And there's different reasons why you might. Let's see. There we go. There's a roll off of paper. That's a paper towel roll. How did they make that, right? They took a flat piece of cardboard and they rolled it at an angle, right? Now, I don't know. I don't think they make pressure tanks that way, but they might. Okay, and if they did, there would be a seam right there, right? No, I didn't measure that with a protractor, but let's say that's 30 degrees. That's why you might do that, okay? So maybe you're going to work for a paper towel company, and you might have to use a biaxial stress analysis of the roll. I don't know. I tend to doubt it, but you might. You just never know. So anyway, this stuff kind of depends on how you fabricate things too. If you fabricate them in a way such that you got planes that are somewhat weak at a certain angle, you might have to check into that. Okay. So that's what we're doing. Okay. So if you're going to do that, it's just a matter of plugging the stuff in, right? You just find sigma x1 for that angle is, what is that angle we're doing? 30 degrees, or what do we got to put in front of the 30? Negative, because it's clockwise, yeah. So little details like that, they matter. So we want a negative 30 degree angle, double it, you get negative 60, that goes into the equation. You run the equations and you get the stresses. So when I do that, I've got sigma x1 is 30, tau x1 y1 is negative 10.4, and sigma y1 is 42. So there's a bit of a sketch of that over there. So on that, at negative 30 degrees, I got 30 megapascals. For the normal stress, 90 degrees off of that, I got 42. And then the shear stress on the 30-degree plane, that would rotate the element clockwise. Okay. So that's negative. That's what's up with that. Okay. All right. So there's a pretty thorough analysis of a pressure tank. Okay? And that's again, I think that's a good example because it kind of pulls in why we do this biaxial stuff, why we analyze it, and kind of that process of when we did the biaxial stuff, I just said sigma x is this, sigma y is that, tau x y is this. Now we're finding ways to know what sigma x and y and tau x y are by doing an analysis of whatever it is we're designing. And we're going to do pressure tanks, which are a little bit obscure. I don't think too many of us are going to design pressure tanks. I mean, some of you might, I don't know, but it's not a mainline thing. But next we're going to do torsion, and that is a much more common thing, especially if you're a mechanical engineer and you're doing shafts that rotate and deliver power. They're under torsion or moment. They have a moment about the center of the axis. We'll also do beams, which of course civil engineers do all the time, or structurals anyway. And mechanicals do too, even though they may not look quite like beams. A lot of the stuff that mechanical engineers design that bear load have some type of beam in them, or a column or something like that. So we'll have a look at some of these other things and look at biaxial analyses based on them. Okay. All right. So All right, so torsion here, what torsion is a twisting action. Very common example of torsion is a shaft, okay? So this shaft, this motor here is going to cause that shaft to twist, and when it starts pumping water here, so what we have in this photo here is we got a motor on this side, and then we got a pump over here. And then by spinning that shaft coming out of the motor, you're going to spin what's called the impeller in the pump and move the water. And you're going to get a twisting action around the center of the shaft. And the term for that is torsion. Okay. So let's have a look at that. Okay. So torsion is the twist about a center of a shaft usually. So there's a central axis on that shaft, and then here's a twist, like that. So that's what torsion is. By far, for what I can think of in the engineering world, torsion is very much associated with motors to me, because you start spinning a shaft and transmitting power in some sense through that motor. So here you see the output of the shaft coming out of the motor. A little different setup there. Previous sketch there, we just have the shaft coming right out of the motor going into the pump. I think that's a pump on the bottom, though I'm not sure. And you've got a fan belt there that's transmitting the power from the motor to the device down there. I think it's a pump. Okay. All right, so motor to a pump. That's a very common setup. Now let's have a look here. So torsion is a moment about the axis of a long, thin member, okay? Torsion commonly occurs in drive shafts. It causes these shafts to twist, okay? Now, when something twists, you get shears that build up. Okay, so think of the shaft as being a collection of coins, like quarters or pennies or something, like a stack of coins. Think like you've glued each coin to the two next to it. If you take that and start twisting one end, as shown, what's going to happen is that glue will give a little bit, and you'll end up twisting a little bit. So had you drawn a line down the middle of the shaft like that, and then connecting to the center, what would happen after you apply that torsion is that line will move, and so it'll twist up like that. Also, you'll get an angle in there, so you get that twist of the shaft on the end coin that you could see. Had you marked a horizontal line on that initially, that'll twist up. So actually you get a couple different twists there, one on the face of the shaft, and another different one that is related but different, that along the outer edge of the outer surface of the shaft, along the long axis. Okay. So when you twist the coins, those lines rotate a bit. And if you have glue in there, that glue would allow that to happen. Now what's going to happen here is one coin is going to try and slide across the face of the other, and that's a shearing action. So torsion is very much related to shear, because you get the coins trying to twist one across the other, and that's going to cause shear. That's the very definition of that. Okay? So when I think of pressure vessels, I think of tension, stretching, like a balloon. And so pressure vessels are very much related to normal stresses, axial stresses. Torsion's different. It's very much related to shear. Okay? Now the central relationship there, if we look at a shaft cross-section, we could kind of look at it like that. Now, of course, I'm still in the notes here. And I'm moving down the road, so where am I? Probably about 580, I think. Actually, yeah, 580. There you go. All right, so first let's define a couple things. Now, a distance from the center of the shaft, which is generally the point about which we rotate, to any point in the shaft would be rho, okay? Greek letter rho. Now, what rho max is the radius of the shaft, okay? So rho is a general distance from the center of the shaft to a point in the shaft cross-section. R is rho max. Now let's put one of these little differential elements like we like to deal with here. Let's call that dA, and let's put a shear stress on that. and put that shear stress at distance rho out from the center of the shaft. Now the torsion then would be the moment of the stress, of the shear stress on that area, times the area, which will get you a force, times rho. So the moment, which will be the torsion, will be the shear stress times the area. Let's say that's a small little area, so let's call that dA. Okay, so a stress times an area is a force. But then we want to add a moment arm to it, which we'll call rho. That would get us the moment of the stress on that little differential element about the center of the shaft. Now, what we want to do for an entire shaft is add up all those possible little differential elements in there. So we end up with an integral over the area of rho tau dA. Okay, that's the fundamental definition that relates torsion in the shaft to shear. Okay. All right, now let's look at a little bit more at this shear relationship. Let's also look at the geometry of the entire shaft here and what happens when you start applying torsion and rolling a shaft. Okay. As I said, let's say we painted or marked a horizontal line down the length of the shaft from A to B, and then another line that goes from B to C. Okay, and then let's apply that torsion. Well, what's going to happen there is point B is going to roll up to B prime, and that's going to take both of those lines and it's going to rotate them, right? And so let's kind of have a look at that a little bit. So that first line is going to rotate up here. That's the line along the length of the shaft. And the line on the cross section of the shaft will rotate also, like so. Okay. So B is going to rotate up to B prime, and I have a point further in on the shaft, E, on the cross section. That will rotate up to E prime. Okay. So I've got rho is the distance from C to E. R is rho max. That's the distance from C to B. B's on the exterior of the shaft, the outside of the shaft. Okay. Now we got a couple angles in here that we could deal with. Let's start with that angle phi that I've got written there. So what phi is, an angle is well, let's see, if I take the radius times that angle, what I get is the arc length from B to B prime. Okay. If I take rho times the angle, I get the arc length from E to E prime, okay? Because the radius times an angle in radians gets you the arc length. So let's take that outer layer of the shaft and let's look at it. And also a layer that's represented by that other line in there that goes from E to E prime. And let's have a look at those just for a minute here. And what we're going to do, we're going to take those layers off the shaft and then we're going to lay them flat on the table and analyze them. So I've got the one that goes from B to B prime, and I'm going to look at another one too, the one that goes from E to E prime like that. We're going to take that layer off the shaft and lay it flat on the table so it's a right triangle. Okay? So what's going to happen are those arcs from B to B prime and from E to E prime are now flat on the table. And so now we can analyze them as though they're right triangles. Okay? Now notice they have the same twist angle on the cross section. In both cases, that twist angle is phi. But these triangles have a little different shape because this one's longer. It's r times phi. Okay. Whereas the one to the right has a smaller leg of the triangle there because what it is rho times theta, okay? So those distances change depending on how far from the center of the circle they are. They're more extreme the further from the center of the circle you are. Okay, so we got the same length on the bottom. It's just the length of the shaft, but we got those two arc distances are different. Right. So one thing to notice here is that the further from the center of the shaft you get, the bigger that distance becomes. Okay. Now these distances here are r or rho times theta. What we also have here is a shear strain. I'll call it gamma. Now what happens, kind of maybe the easiest place to see that is if you start with a little bit of a square element there in the right angle at the bottom of the triangle. If you rotate that up, that's not going to be a square element anymore. That's going to turn into a rhombus if you rotate that up. Okay? So there's a square element. When I rotate it, it turns into a rhombus. Okay? That's what's going on there. Well, that kind of fits into our little shear angle thing, because what we've got is we have a rhombus like that that's kind of shaped like so. But now if I draw an angle, a line perpendicular to this one, I'm going to have a little bit of shear strain in there, okay? I'm calling that gamma. That equals that. Those gamma angles are the same. Now they're going to increase as rho increases. So there's a constant ratio between that shear strain and how far from the center of the circle you are, which is rho. Okay, so gamma over rho is a constant. So what we got here so far is just this basic relationship here that the further out from the center of the circle you go, the bigger the shear strain is. And you can kind of see that shear strain relationship when you rotate those points up. Okay. All right. And that's how we can develop these equations that we use for analysis, because we got gamma over rho as a constant. Okay. Now, as long as we're within the proportional limit, G is tau over gamma. So tau, the shear stress, is G times whatever gamma is. Okay. So not only is gamma over rho a constant, if we multiply through by G, tau over rho, the shear stress over rho is a constant. So the further out from the center you go, the bigger the shear stress. Now we can plug that into some of our relationships here to get the equations we use to design and analyze these shafts. Okay? Because the torsion is the integral of rho tau dA. We developed that earlier, where if we look at a little element there and find the force, which is the stress times the area, multiply that by that moment arm rho, we get a torsion. All right. So we got this basic relationship here. Now what we know is that tau over rho is a constant. So what I can do is I can put in a term of rho over rho into that expression. That's just 1. That's not going to change anything. But then I can rearrange it so that it's tau over rho times rho squared. And the reason I would do that would be to get the tau over rho, which is a constant, out of the integral. So I end up with the torsion is tau, the shear stress, divided by rho, the distance from the center, divided by the integral of rho squared dA. Okay. Now what that is a polar moment of inertia. If you remember from statics, what a moment of inertia is, it's a distance squared times an area. So that's a polar version of that. So I can put I in for that. Often I subscript it with a P, meaning polar. So the torsion is tau times I sub P over rho. Now what I'm interested in is solving for the shear stress. So the shear stress, when I solve it out, is the torsion times rho over I. The maximum shear stress is the torsion times R over I. Okay. So that's design equation number 1. Okay. And normally we use this one. So if you want to know what the maximum shear stress is in a shaft, take the torsion, multiply it by the outer radius to the outer layer of the shaft, divide by the moment of inertia. Okay. So that's one thing you design on is the shear stress, because when you have torsion, you get shear stress. The other thing you design on is how much this angle in the shaft twists, because that can throw things out of alignment when you've got moving devices. Yeah, I'm out of time, so we'll just hit that next time. We'll just do that. I'll get you a couple of these to do, though. About 251 and 253. And what's going on here? So we have a couple more that are due Monday, so we'll make these due Wednesday, okay? I think that'd be the thing to do. Yeah, I think so. So today is Thursday, so that'll be the 12th then, right, for Wednesday? All right. There we go. We'll finish this up tomorrow.